of the cylinder, I'm going to ignore that. I'm going to ignore the curved part of the cylinder. I'm going to instead look at the end faces and calculate the electric field based on that. Now we have two surfaces, so we have two areas right here. We have the area on the top, we have the area on the bottom. Now, if we look at this and we calculate Gauss's law once again, E times A is going to be equal to Q over epsilon naught. But here, the surface area over here is going to cancel out with the surface area that was over here. It becomes even easier. And our final result is that the electric field is equal to sigma divided by 2 epsilon 0. This means that the electric field is unchanged. It doesn't depend on the distance here. But again, we're assuming an infinite sheet of charge. If we had a finite sheet of charge, if we got far enough away from it, it would begin to transition to a 1 over r squared type dependence. Again, here we go, Q over epsilon 0. We have sigma A as being the charge per unit area times the area. That replaces Q. Two surfaces, a top surface, a bottom surface. Okay, and then that's our final result. Okay, this is a really important type of geometry that we're going to come across in later chapters. It's what's known as a parallel plate capacitor. And with a parallel plate capacitor, you have a positive charge and you have a negative charge. Now, if I did a Gaussian surface around this whole thing, the net charge would be 0, and thus the electric field on this side and this side must be pretty close to 0. Okay? But let's do our Gaussian surface for a flat plane once again, but we're going to do it for a positively charged surface and a negatively charged surface. Remember this 2 right here in the denominator? If I use two surfaces, okay, I double the electric field, and thus the electric field between a parallel plate capacitor is sigma divided by epsilon naught. It was 2, but again we have two plates. The positive plate contributes a positive charge downward. The negative plate also contributes an electric field in the same direction. I get this as my electric field. Okay? So it shows that the electric field between two plates depends on how much charge is there, really the density of charge.